Hello everyone, welcome to my channel. So in machine learning, we cannot do training if we have missing data. So in general, we have two ways of dealing with them. The first one is to remove them, and the second one is to impute some values to our missing data. Sometimes we just take the simple way and impute all the missing data with 0 or 1 or -1 or 999, for example. And sometimes if we want to go beyond that, we would apply some statistical models that would generate some values to be imputed. And now, in this video, we're going to try to analyze and learn the model from a time series with some missing data. And beyond that, we're going to also impute some values in them. This is all possible using dynamic linear model, which is using Bayesian forecasting. So let's get started. Now let's talk about the use case for today's video for a bit. So we're going to talk about PM 2.5. We're going to take the data time series of PM 2.5. PM 2.5 is particulate matter, which size is 2.5 micron or even less. So it's an extremely small particle that fill up the air. These particles might be dust, ash, or toxic metals. When we inhale them, it would get stuck in our deepest part, the deepest part of our body, and stay there. So it's unhealthy if we inhale too much of them. PM 2.5 is now considered as the most common cause of health problem related to respiratory system. And PM 2.5 is also used as an indicator of air quality. PM 2.5 now can be measured using sensors located in certain locations. There are many organizations now throughout the world which organize this. So they usually plan the location for each sensor, and then they also manage data collected from these sensors. In Bogota, the capital city of Colombia, there is this organization called RMCAB. This organization spreads out some sensors throughout Bogota to collect some data about PM 2.5 and other pollutants. And we're going to take the PM 2.5 time series data from this organization for today's video. So to get to the data, I show you two links here. The first link is actually getting you to an interactive map where you can get the real-time measurement of air quality. And of course, some other measurements like PM 2.5 and other pollutants. But to get the data that we want to use for today's video, we need to click this link. And it will get you to this page. Okay, so we have a menu here. It's in Spanish, but of course you can always translate it to English. If you understand Spanish, then good. Anyway, so in the lower left here, we have options of stations. And for today's video, I'm going to choose USME. So check that. And then we're going to take the period annually, but for 1 hour. So choose the time period, the starting period, which is, I'm going to choose from January 1st, 2021. And then the ending date, the ending period would be set automatically, which is January 1st, 2022, but at midnight. So it's a full year, all the times in 2021. And then the report view, you can just click the Excel to get it right away, but I want to show you a little bit about the data. So I'm going to choose with the default report. And then you can just click show. In Spanish, it would be mostrar. I don't know if I pronounce it correctly, but yeah. So the data that, oops, it's all right. So the data that you will see here, that you see right now, you're seeing right now is what will you see in the Excel page as well. So including this type, average, in Spanish though, the data set will be available in Spanish. So the data, the variable name only starts at the fourth row. This will be the fourth row, and then the fifth row is the unit. We don't want that, so we need to remember that when we read it in our R programming, we want to skip the fifth row, and the data starts at line 6. And then if you scroll down, you see that you have 8760 items. In other words, we have 8760 data points here. So the data starts at line 6 and then ends at the 8766, line 8766. What is there beyond that? So after the data, you have a little summary, like the minimum of each variable, and then the latest state, the earliest state, and then the latest date, and so on. So because we don't want that, we don't need that in our analysis, so make sure that we don't read it. Okay, so we're back in our R programming. So yeah, before we do anything about the analysis, let's load the packages first. So the first package here is for opening the Excel file, and then deployers for preprocessing, and then plotlist for visualization, and DLM is for implementing DLM, or dynamic linear model. Okay, now let's start reading the file. As I said earlier, the variable names are stored in the fourth line 4. So we need to set the start row to be 4, and then the rows that we want to read is 4 and then 6 until that. And I'm going to load the data now as USM. So remember that we are taking the data from USME station. So yeah, I'm using the first 3 letters here. Okay, let's run this. Okay, now I'm going to show you what the data looks like. Okay, so the date time doesn't have the name right now because the name date time is on a different line. So yeah, R just give the name by default X and then the number of the column. Okay, but one thing to notice is that the class of all variables of all columns here is parsed as character instead of POSIX or datetime class and numeric. So we need to change that actually. Oh, and by the way, the precipitation column here is all missing values. So we're going to remove this column as well. Okay, so there are 2 main things we need to change. The first one is to change the class of the columns, and the second one is to remove the column of precipitation. So this line is to convert the class of the first column, so that we will have datetime class. And then for the rest of the columns, I converted as list first, so that the data frame would be a list of lists. And then at each of the lists, I will apply a function as numeric. And then after that, I convert it back to data frame. So from list to a data frame again, and then combining it with cPoint function of date time and the new and improved data frame. And then lastly here, this line is for removing the precipitation column. Okay, I'm going to run this. Okay, this warning message is obtained after running this line. But don't worry about that, because the data naturally has missing values, not only in PM2.5 but also in other variables, in other columns. So NAs must be there. Okay, now let's see the clean data. Okay, the data has 8760 values, just as you have seen in the website. And then the class of the column has changed. And we have only 13 columns now instead of 14 because we have removed one. And also the date time column has changed from X1 to date time. Okay. Now let's make a time plot for PM2.5 since it is our focus. So this is the code I'm using Plotly. Okay, so I have a warning only because I want to show you clearly the y-axis label, and I need to use latex for that. You might not need this if you run it in your own machine, but yeah, I need it. So I'm going to run this. I mean, it doesn't affect the plot whatsoever. It only affects the y-axis label. Okay, so here's the time plot of PM2.5. The unit is mu gram per meter cubed. Okay, excuse me. And now, as you can see, without even zooming in, we can see there are some gaps in it, like here, and then here, and then also here. Let's zoom in one of the gaps. So yeah, oh yeah, here we have a little gap as well, but it's very little, maybe only one missing data. While here, we see that the sensor started to went off on April 1st, midnight, and then only get back on April 5th. So we have 4 days of missing data, or equal to 96 data points in a row. That's quite long. In machine learning, in normal or, well, yeah, traditional method, you won't be able to do anything unless you impute some values to it. But sometimes we might need to still get to see what happened here. What is the model? What is the model that could capture the time series of PM2.5 in Station Usme, Bogota? And we will do that with DLM. Yeah, so we're coming back to this time plot again in a moment. But now let's look at our code again. Now let's talk about DLM briefly. So DLM, or dynamic linear model, is a specialized case of state space models. State space models has this representation of a quadruple of F, G, V, and W. F and G are the sort of like the coefficients, and then the V and W are the variance matrices. Okay, and DLM looks at time series in two hierarchies. The first one is the observational level. So all the values that we see here in our time plot are in the observational level, sorry. And the second layer, which lies beneath that, is called the system level. So it's believed that the system level is the one that generates the value for the observational level. Of course, we have some variation in it, like the error term. That's why V and W is still used. Okay, now in dynamic linear model, we have dynamic. It is dynamic because the state vector values, or like you can think of it as the coefficient values. The coefficient values and the variances can change over time. And then with linear, it's called linear because we can just add the basic models which capture every component in a time series. So basically, the model that we're going to use is made in only one line, which is this line 40. It's only take one line. It only takes one line to make a model that we need. Yeah, but we have three components. So the first one here is the polynomial model of order 1. And then the second one, trigonometry. Trig is for trigonometry. And this is used for capturing the cyclical pattern of the PM2.5. And then lastly, it's a regression model. So we are analyzing one time series using another time series. Okay, now let's dive into each of the components. So polynomial model of order 1. Here is the definition. So the quadruple representation is 1, 1, V, and W. It means that both the F and G has only one value, and the coefficient is 1. And then V and W. So polynomial model of order 1 is sometimes called as a local mean level model, and it's the most basic model in DLM. To make it even simpler, we assume that the variances across time over time didn't change or constant. So sometimes it's also called as constant model. So that's why in our quadruple definition, we don't have the index t. We just have V and t. Okay, now I said earlier that DLM looks at a time series in two hierarchies, the observational and the system one. So that's why we have two equations here. Okay, the first one is for the observation and the second one is for the system. So you see that the first one here, yt is the, well, in this case is the PM2.5 value that we see in our time plot, is modeled as mu t. Mu t is the local level, the mean level at time t, at that time step, plus some error term. And that mean level is modeled in the system equation, in the system level, as the previous mean level, plus some error term. The error term, both in the observational and the system level, are normally distributed. Okay, and the initial information here is for getting the iteration going. So we are using Bayesian forecasting, right? And in Bayesian forecasting, we need a prior and posterior, and then that posterior would be used to update our prior and so on. So to get the first one going, we need our initial. So why are we using this for this case? Let's look again at our time plot. So if you see at a glance, the PM 2.5 level doesn't change much. I mean, it doesn't have an upward growth or an upward trend or downward trend. I actually made some videos about DLM here. Especially I discussed about gold price. And if you see that video, you will see that the gold price has a really clear upward trend. But not in this case. In PM 2.5, we don't see it that clear. So I thought, yeah, I guess a polynomial model of order 1 is the most appropriate for this case. But we see that there is some kind of up and down that forms a pattern, like a cyclical pattern, especially if we zoom in. It's really clear, up and down, up and down. The cyclical pattern is really apparent here, like here. So we need a second component to capture this seasonality. And we are using that using the Fourier form representation of seasonality. Okay, so in R, we can apply Fourier form representation of seasonality by using this function DLM mod trigonometry, and 12 here is the period. Let's say that if we have a very simplified time plot of PM 2.5, so the y-axis here is the PM 2.5 level, and the x-axis, the y-axis is the PM 2.5 level, and then the x-axis is a t. And well, so we can think of PM 2.5 here as the function of time, right? Let's name the function is called g. So g of t. At time t equals 0, here, g of 0 is at that level. And then since we've decided the period to be 12, so that when time is 12, in other words, G12, the PM 2.5 level at time t equals 12, or in other words, G12, would be equal to G0. More generally, G0 would be equal to G of the total cycle it has completed times the period. The period is 12 here. So G0 would be equal to G12 and then equal to G24, G36, and so on. And then similarly, G13 would be equal to G1. We can have this vector of what we call a seasonal vector. So that if we ask what is G50, we can divide 50 by 12 and then take the remainder of it, which is 2. And we know that we need to take the index 2 from our vector to get G50. This is why we have a seasonal factor from J. So J, in this case, is going from 0, bad handwriting, 0, up until, in this case, is 11. Or more generally, from 0 to p minus 1 because we need p values to complete the cycle. So every time we ask ourselves what is the function or what is the value of PM 2.5 at time t, at time 75, at time 34, we always need to look at the seasonal factor, right? So at the observational level, yt is modeled by a seasonal factor of j. And of course, j is the remainder that we've got after dividing p by t. T by p. Okay, and then the seasonal factor can be also modeled in the system level as this. So A0 plus okay, so this is the equation for the seasonal factor. I want you to notice several things. The first one is it is a linear combination between the cosine function and the sinus function. The cosine will always be mentioned first. So this A, the cosine coefficient, is always for the odd numbers of j. So j equals 1, 3, 5. The first j, and then the third, and then the fifth, and so on, would be for the cosine coefficient. For the rest of them, or the even coefficients, would be for the sinus coefficient. A and B are called Fourier coefficients. Now, A0 is defined to be this, and then A, R, and B are respectively defined as this, and then B0 is defined to be 0. Okay, now I want to tell you what is H here. Okay, R is going from 1 until H, right? And H, what is H? H is the harmonics. H is the harmonics, and H is defined to be P divided by 2 if P is even, which is the case for today's video, which is the case for now. P is 12, right? So we have 6 harmonics. We can think of harmonics as waves. In other words, we have 6 separate waves, 6 different waves with different frequencies. If we add them up, we will get the seasonal factor. That's the idea. The introduction of R, the harmonics, is necessary and more convenient because the DLM definition to capture the seasonality pattern using trigonometric functions or periodic functions is based on each harmony. So we have 6 harmonics right now. So we will stack the DLM definition for each harmonic. Okay, and here is a formal definition, and you can see that for any frequency omega here, omega here. So omega, the frequency omega is defined to be 2 times pi. The omega of the rth harmonic. So 2 times pi times r divided by period p. I'll just discuss the special case first. So when r equals 6, we have 6 harmonics, right? When we reach the 6th harmonic, the omega 6 would be equal to pi. So for even number of period, the last harmonic would have the Nyquist frequency here. So for the last harmonic, we would always fall into the next group, fall into the second group. And so, for the sixth harmony, the DLM definition for the sixth harmony is only defined to be this. The F matrix, I need to zoom in for a minute. So, the first one, the value 1 here is the F. We have only one value and it's 1. And then this is for the G. And then the double dots here are for V and W. But for the rest of the harmonics, so for the first 5 harmonics, harmonic number 1 until number 5, for each harmonic we have two subcomponents, let's say. So recall that we have seen the cosine function and the sine function when we define seasonal factor, right? And that is used for the first 5 harmonics. So when R equals 1, 2, and then 3, 4, and then 5, up until 5, we put this. We define the DLM for harmonic 1, 2, 3, 4, 5 with that. So E to the index 2 here is to indicate that we have 2 dimensions. So now if we want to combine all of them, by the way, the E factor here is defined the F matrix in the general DLM definition that I have mentioned earlier. So if we want to combine all the harmonics, the E, or well, the F, let's say the F here would be a concatenation of each harmonic. So 1, 0, and then 1, 0, 1, 0, repeat itself until the last element is 1. Like that. So the first 1, 0 here is for harmonic number 1, and then the second 1, 0 is for harmonic number 2, and so on. And the last 1 here is for the Nyquist frequency or for the last harmonic. Well, I'll just explain this for a little bit. So for the G matrix, the matrix that we have defined for each harmonic is going to be put in the diagonal matrix of G. And then -1, of course. -1 is the last element, the last entry of the last diagonal matrix. Why are we using period 12? Okay, to take a look at that, we need to zoom our time plot here. So, okay, so I've zoomed in the time plot to the daily basis. Okay, so like from here, this is the peak here is on January 31st, 4 p.m. And then we reach another peak at the next day, 3 a.m. So it's almost 12 hours after that. And if you look carefully on the time plot, most of the time, the peak repeats itself every 12 hours. Of course, that's not always the case though. Sometimes it takes 14 hours or even more. And sometimes it's not really clear when is the other peak, when is the next peak. So let's say that this is February 4th, 9 a.m. This is the first peak, and then it's not really clear when is the next peak. 9 a.m. and then maybe the next peak is here. It's the next day, 2 p.m. So it's even more than 24 hours. Or perhaps like this, February 6th, 12 p.m. and then the next peak is around here, February 7th, 2 a.m. Here, from this peak to the next one takes 14 hours. So yeah, when I scroll down the data, scroll like to the left here, it seems like the pattern repeats itself every 12 hours, roughly. So that's why I set the period to be 12. Of course, when we tried out the model later, we can try to play with some periods value. Now, let's go to the next component. So the next component here is regression. I'm using this component because I think to make my prediction of the missing values in PM 2.5 more robust, or like instead of relying completely on our series, we can also try to use other series. That's what I thought. And yeah, so in package DLM, we are applying the regression model, dynamic regression model with DLM mod reg. Reg is for regression here. And the input is the regressor, which is X. I'm using only one regressor here. So that's why I have only C, or actually I don't need C point here. I just realized. Okay, so I want to tell you about the regressor. So the regressor we are using here is PM10, which is particulate matter, but it is bigger since the size is 10 microns or less. Yeah, X is only of one variable, and since I set the intercept to be false, so this regression model would be a regression through the origin. So the model definition would be more simple. It would be even simpler. But of course, we can try out some alternatives. Like I can try to make it true and see how the model performs. Okay, so this is the definition of regression model, dynamic regression model. So the quadruple representation is Ft and then 1. So the matrix G, the system matrix G, is only 1. And then it's only one value, by the way, one value, and then the value is 1. Okay, so does Ft. Ft is actually like a vector because we have only one variable here. But each time it would change. And Ft is the regressor itself, the regressor value. And then of course we have Vt and Wt. In R, we will assume that V and W is constant, so we don't need T actually here. We can just omit the T. So Ft, 1, V, and then W. Okay, and so once again, we have two equations. The first one is the observation equation. So Yt is modeled as Ft times the state vector, theta t, plus some error term. And then the state vector, theta t, is also modeled in the system layer, which is the previous state vector plus some error term. The error terms are still using the same assumption, which is normally distributed with variance as written here. Okay, but the caveat is that if Yt can have missing data, Ft or the regressor cannot. So if we have missing data in the regressor, either we need to impute it, or there are some, or we model them as well. So we include the regressor in our modeling hierarchies. it's gonna be just a little bit more complicated. So I'm going for the simpler one, which is imputing all the missing data in the regressor with 0. Okay, so we're back here. The x here, as you can see, that's why I'm using replace function. So we are replacing the NA values with 0. So in the replace function in R, the input is first the factor that you want to replace, and then the second is the index which you want to replace, or exactly where we want to replace it. And then this is the value which we want to impute. Okay, now that we're done discussing about each component of the model, of the big model, now we can do adding them together into a big model. So as I said earlier, by adding these components, we are actually stacking the matrices or stacking or concatenating the vectors into a large matrix, a large vector. That's what we're doing here. So in polynomial model of order 1, we have only one variable. The state factor will be of only one variable, one element. And then DLM mod trick would have 11 variables. And then for the next one, or the next component with it, which is the regression, we have only one variable as well on the state factor because x is only one regressor and we didn't include the intercept term. Okay, so let's run this. Yeah. So by running line 40, we are building the model. We have not trained it yet. And now, okay, by the way, polynomial model of order 1 has one variable, and then mod trick has 11 variables, and then the mod regression has also one variable. So the total variable should be 13. So yeah, 1 plus 11 plus 1. Okay, so yeah, as you can see, it's like this. And then line 42 is where we train our model. In other words, we update our inference of the state factor and the variance. We are using DLM filter function, and the input is the time series that we want to train and the model that we've just built. And then to check our model performance, we are using mean absolute error. But in calculating that, we are excluding missing values in the time series. Oh yeah, the forecasted value. So in DLM filtering, we update our state vector or our model coefficients, and then generate a one step ahead forecast. And that forecast is what we are going to use for to be imputed to the time series. And so it's like using our prediction of the next data point. So we want to calculate the mean absolute error between the prediction, the one step ahead forecast, and the real value. So the mean absolute error, if we are using a model like in line 40, is 3.058. Okay, we can try out some other models. Let's say that we add the interceptor now in the regression model. Let's build that model again. Now, since we've added our intercept term, the variable adds 1, so that we have 14 now. And the mean absolute error after by using that model is 3.05. It's exactly the same. It doesn't change. And yeah, by using the principle of parsimonies, we want to be able to explain our time series as well as possible by using as little variables as possible. So, okay, I'll just stick with the non-interceptor. Okay, and then another model I want to try is not using x at all, which is relying completely on our time series. Okay, if we use that, if we don't use any regressor, the mean absolute error would be higher, a little bit higher though, 3.08. We got 3.05 earlier, but now we got 3.08. And then we can try out some other models. For example, the intertrigonometry. Maybe we want to change the period, for example. Like maybe 14. If we change the period, we will get much higher MAE. Okay, I guess among these models that we've tried so far, this is the winner. So we're going to use this. Okay, now let's plot our forecasted value. It's actually not a forecast, but it's more precise to say that it's the mean of the forecast distribution. Okay, so we're going to plot the data and the mean of the forecast distribution. So as you can see, the mean of the forecast distribution sometimes negative. So yeah, if we are using these negative values as our imputed data, it's gonna be a little bit weird actually. But anyway, let's see it first. And these negative values, in my opinion, could be generated because we don't have any data. But it's not always like that. Sometimes in here, around here, the prediction is still above 0. And it's going pretty well. Look at this. So the gray area is around here. And then imagine that we are following the yellow line here. It's very low. And then it started again at this level. I think it's quite decent. Let's try to move around the plot. As you can see, the yellow line is doing pretty well in predicting the next step ahead because it's following the dots. Okay, so let's see that around August 2021, we have a big gap here as well. But the prediction is quite well. I mean, very little of them are below 0. Let me save it first. Okay. So maybe we can deal with this by taking the absolute value of it. Of course, we are taking the absolute value of it after the filtering process is done. Okay, because otherwise the filtering process or the training process would be interrupted. Let's run this. So imagine that we want to give the full data, the imputed and the raw ones, to the organization or to any stakeholders. We want the value to to be making sense, right? So yeah, if you see at a glance, we don't have any values that is negative. And then let's zoom again around here. Because this is I think this is the longest data gap. Okay, as you can see, no negative values. Okay, so lastly, if we want to make our data, we want to combine into a complete data, we can do that. So I've made a function to do it. So essentially, we are taking our vectors, the raw data and the imputed ones. The imputed ones here, the imputed is the mean of the forecast distribution. Okay, and we are only taking the value from the IMP vector if the data in the raw vector is NA or not available. So this is what this function is doing. Okay, and then yeah, this is the code. Oops. Oh, sorry, I haven't run the make data definition. Okay, so that's it for today's video. Don't forget to subscribe, like, and share this video. All the code here will be uploaded in my GitHub, and I'll give the link in the comment section below. Okay, so once again, thanks so much for watching. I'll see you next time. Bye bye.